right, how's everything going?
Reasonably well.
Reasonably well. So, things I've posted. So Monday I posted your second programming assignment. So this is a C program that basically prints out Pascal's triangle. Okay, so we talked about Pascal's triangle. The main characteristic that you need to keep in mind about this is when you want to do Pascal's triangle, the first row is just a 1. Second row is a pair of 1s. Every row after that begins and ends with a 1. And every number in between is the sum of the two numbers above it. So 1 plus 1 is 2. Next row begins and ends with a 1. This number is going to be the sum of the two numbers above it. 1 plus 2 is 3. 2 plus 1 is 3, and so on. And I want you to do it like that. Okay? You can find the entries of this using combinatorics. You can do n factorial over r factorial n minus r factorial, but it's going to blow up on you. Okay, if you try to do too many rows. So don't use factorials to do this. Use this property that each row starts and ends with a 1, and every number in between is the sum of the numbers above it. And it gives you some practice thinking about indices on arrays and how do you get to the two numbers above you and copying arrays and things like that. But it's not too bad if you go at it with this approach. You don't need to format it so it actually looks like a triangle that's symmetric. You can start everything on the left if you like. That's perfectly fine. So that's what your program needs to do. Your submission is a PDF file, okay? Your PDF file has two pieces to it. The first piece is the source code for your program. The second piece is the output when you run your program. So I'm not going to compile your program and run it myself and stare at the output. I want you to take your program, compile it, run it, generate the correct output, and then make a PDF document. Okay? Your PDF document contains a copy of the source code of your program, and it contains whatever output your program produced. So use your favorite word processing approach and put those together into a single document, save it as a PDF. That's what you upload to Canvas. Okay? So that's all specified in here, but just to be explicit about that. Right, single PDF containing source code and program output. If you decide to cheat and just type these numbers in by hand, type them in correctly, because every now and then I get a submission on this and it's got Pascal's triangle, but there's a 162 instead of a 126 in the middle, and it's a dead giveaway. So, but better yet, just write the code and have it work. It's easier. And if you do this, so I only want the first 15 rows, but you should be able to run this much further than that before it blows up, right? Because these numbers grow relatively small, relatively slowly, so you can experiment with that. So is that clear? So I put that up late Monday, so I'm giving you until December 4th, which I think is sometime Tuesday, right? All right, so that's one new addition. The other addition is I've posted a homework related to graphs. And this I would like you to start working on before Friday, so that Friday you can ask questions about it. And then it's due on Monday. So these are from the supplemental exercises in the text. Question 1 should be pretty straightforward. Question 5, go ahead and do parts A and B. I don't understand what they're asking for in part C. Maybe you do, but don't worry about part C. And then question 14, I don't want you to do the question as it's written. I want you to just take the graph from question 14 and run Dijkstra's algorithm on it. So it's an easy place to find a graph.
You said just 5A and B?
5A and B. So let me just pull this up. Okay, to do question 1, which is looking at isomorphisms of graphs. So think about those, and it says give an explicit isomorphism between the graphs that are isomorphic. That means give me a bijective function from vertices to vertices. Right, that's our definition of isomorphic. One-to-one onto mapping from vertices here to vertices there that preserves adjacency. So do that for question 1. Question 5, you're building a neighborhood map out of a Central American map. So go ahead and do A and B, and if you can figure out what they want for C, cool. And then question 14, ignore all of this stuff. Okay, just take this graph and apply Dijkstra's algorithm to find the shortest path from A to Z. So when I ask you to do a Dijkstra's algorithm, getting the shortest path is not the goal. Okay, if you write down in big bold letters what the shortest path is, that's not what I'm looking for. What I'm looking for is a demonstration that you understand Dijkstra's algorithm, which means I'd like to see the steps that you're using to get to that shortest path. And if you have a graph and you do something like right, like this, and then you end up, A, C, D, F. I can't really look at that and tell what you did, okay? When we run Dijkstra's algorithm, we do this continual relaxation of nodes. We find tentative distances from a node that's our current node, and if it's smaller than the previous tentative distance, we relax the node, we change the tentative distance, and we record that new path. But if you just kind of cross these things out and scribble them, I can't tell what you did. Okay, so you want to find a way to make it clear as you're applying this algorithm what's happening when. So one possibility is to use a really big graph and just work really, really neatly, right? And annotate, like, step 1, this is my current node, and we'll put some distances here. And so step 1, we would say relax the distances from node A, so this infinity will become a 2, and this infinity will become a 4. Okay, at that point it's clear to me what happened, right? You had an infinity, you crossed it out, you made a 4, you had an infinity, you became a 2. You were working with this node. And then, you can even do this to say that node's been visited. But the next step is to find the node that's closest to A and make that your current node. In this case, it's going to be C. So if you draw a box around C, I don't know which node you circled first, right? So at this point, I would leave this as is, make a copy of it, and go ahead and make your changes on that copy. So you're getting kind of a time sequence of graphs. Does that make sense? And then I can look at it and I can say, okay, this was the first set of things you did, and the second set of things will look like this, but you'll have this underlined, and this will be a 2, and this would be something, and so on. And then, right? So when you're done, think about what you wrote and say, can you look at this and unambiguously tell the steps that I applied to get to the answer? Okay, that's the goal. And I think the best way is to just redraw the graph. And yeah, it takes a little while, but it does.
Do you want us to redraw the graph after every step?
Anything that, if you're going to make more than, anything that's ambiguous, right? So you start off with node A, and it's your current node, and you relax, and it's done, so you mark it visited. And now you need to find the next node that you're going to make your current node, right?
Could we just draw a bigger graph and then also put like a description of where we went second?
Yeah, you can do it on a really big graph if you start numbering your steps in a way that makes it clear. That would be fine. And it would save you from redrawing. But you can also just print a bunch of copies of it. And like I say, when I give this to you on a test, I usually give you a few pages that have multiple copies of the graph, so you can work on it. So find something that lets me see the process. All right, and then I also want you to do question 4. Because it looked interesting to me. And I don't actually know how it comes out in the end. So it's a weighted graph, right? Your vertices are labeled with numbers, and you think of those as cities, and so you define an n by n matrix that represents this graph. So those weights tell you the number of routes from one city to another. So there's 4 routes that you can take from city 2 to city 4. There's 2 routes you can take from city 1 to city 4, and so on.
Right.
So you build up a matrix. It's a 5 by 5 matrix, and entry 1, comma 4 would have the number 2, saying there's 2 routes from 1 to 4. Entry 4, comma 1 will also have the number 2, and the diagonal will have zeros. Okay, so aij equals 0 if I equals j. Otherwise, aij is the number of ways to get from I to j, which is given to you by the weight. So you make this matrix A. It's a 5 by 5 matrix. Okay, so I want to see that matrix. And then part B, it says calculate what A squared is. So A squared is multiplying A by itself as a matrix. So how many people here know how to multiply matrices? Okay, so I'm going to run through that really quickly. And then part C, I don't know what the answer is. I haven't done this myself, so I'm curious what you come up with. So interpret the meaning of the entries in A squared. So A squared is going to be another 5 by 5 matrix. And so think about the 5 by 5 matrix you end up with and how it relates to something on this graph. And we'll talk about it after you're done. So matrix multiplication. Okay, there's a 5 by 5 matrix. That's presumably random, but nothing is random, so maybe I should play lottery tickets. And this is just an example matrix. Okay, so we want to multiply these, and we're going to get a 5 by 5 matrix. Okay, so here's how you do matrix multiplication. We want to find this upper left number in this product matrix, right? So it's row 1, column 1 that we're looking for. Okay, so row 1, column 1. To find that, we take the first row of this matrix and the first column of this matrix. And we do what's called a dot product. So how many people remember dot products from physics, if you've done physics? Okay, so a dot product says multiply the first numbers, multiply the second numbers, multiply by the third, multiply the fourth, multiply by the fifth, and then add up all of those products. Okay, so this first entry is going to be 2, 4, 1, 3, 6, dot product 2, 1, 7, 1, 5. And I'll expound on the dot product separately. So row 1, column 2, we're going to take the first row here, and we're going to take the second column here, and we're going to take their dot product. So this is going to be 2, 4, 1, 3, 6, dotted with 4, 4, 6, 1, 4. Right, these are vectors. These are 5 numbers. It's not a 24,000 number. Okay, and we do that all the way through to get all 25 entries in this matrix. So let's pick one from the middle. Let's take row 4, column 5. So we take the 4th row and the 5th column, and we take their dot product. So it's 1, 1, 6, 4, 3, dotted with 6, 3, 9, 3, 8. Okay, just some example points, but hopefully enough that you can reproduce this later. So dot products work like this. If you want to do 2, 4, 1, 3, 6 dotted with 2, 1, 7, 1, 5. So it's 2 times 2 plus 4 times 1 plus 1 times 7 plus 3 times 1 plus 6 times 5. Alright, so there's your 6, there's your 5, here's your 3, here's your 1, there's a 2, there's a 2, and so on. Does that work for everyone? Or you can plug them into your calculator and just hit the multiply button and get the product. But you should know how to do these by hand. All right, so that's question 4. So questions 1, 4, those first 2 parts of 5, and then do Dijkstra's algorithm on number 14. So 4 questions basically. So try those before Friday, and then we can talk about them more during Friday's class. All right, so there's more we can say about graphs, but I'm going to switch topics on you. The next stuff we would talk about with graphs is basically related to things that we call trees. Trees are a particular type of graph, but we're going to talk a lot about trees in CSE 222. So we'll be getting to those in a couple of months probably. So I'll leave graphs with where we are for now. And I want to change topics. So this is the last sort of broad topic that we're going to cover in here. So this is languages and grammars. And languages and grammars will take us into things like state machines, and it will take us into Turing machines and questions of NP completeness and the halting problem and all kinds of strange open questions and disturbing theorems, which is a good way to end the course. So let's start with languages and grammars. So the first thing we want to nail down is syntax versus semantics. So syntax is, roughly speaking, the structure of something, right? The syntax of a C program says you got to have a semicolon at the end of a statement. If you have an equals statement, you need to have a variable on the left, and you need to have some sort of expression on the right, right? So you can't say x plus 2 equals y. It'll give you a syntax error. So syntax is just the structure of something. Semantics we can think of as the meaning of something. So here's an example of a syntax error, right? if parentheses minus equals plus, right? With a nice curly bracket at the end. The compiler will throw up on that, right? It'll point to that line and it'll say there's some sort of error there. It doesn't fit the structure of a C program. Okay, so this is a syntax error. This, the compiler will very happily compile. There's nothing wrong syntactically with this, but semantically it's questionable. Because why would we make an if statement if 1 equals 2, do something? 1 is never going to equal 2. Right? So this, we could say, might have a semantic error. Or maybe it's just a clever way we made of commenting out a section of code. And then we want to comment it back in, we can change it to if 2 equals 2 or something. But in terms of the meaning of this statement, right, the semantics of it is somewhat questionable, but the syntax is perfectly fine. Okay? We're only going to be talking about syntax. We're not going to worry about semantics. So everything we're talking about in this section, we're looking at the structure of sentences or languages, as opposed to the meaning of them. And so we'd like to have a way of working with what we can call a formal language. So formal meaning that somehow it's more than just that sounds like a good sentence. Or I don't think I understand what this person is saying. We'd like a way to define what is or is not syntactically a valid sentence. And sentence will mean more than just a spoken or a written sentence for human communication. It's going to extend to statements in a computer program or entries in a Turing machine's operation or other things, but we'll use the word sentence kind of generally. So here's an example of a formal language. So we can define a sentence to be a noun phrase followed by a verb phrase followed by a period. So I'll put a plus in here. I'm going to be kind of flexible about how I represent this. So a sentence is a noun phrase followed by a verb phrase followed by a period. A noun phrase can be defined as an article plus an adjective plus a noun, or it could be an article plus a noun. A verb phrase is going to be either a verb followed by an adverb or just a plain old verb. So our goal is to define what is and is not a sentence. So that if somebody gives us some collection of symbols, we can say that's a valid sentence or that's not a valid sentence. Okay, and ultimately this is all we're doing. We're analyzing collections of symbols. And that's what you do when you read a book or when you read a homework question. You're just taking in symbols and analyzing them. So first part is to look at syntax, right, which is our only concern. So given something that we claim as a sentence, we want to know, is this actually a valid sentence or not? Well, this definition lets us break the problem into subproblems. Given a collection of symbols and we want to know if it's a sentence, we can simply say, is it a noun phrase followed by a verb phrase followed by a period? Okay, this is going to be recursive eventually. How do we know if this thing is a noun phrase? Well, is it an article followed by an adjective followed by a noun? If it is, it's a noun phrase. If it's not, we could say, oh, is it an article followed by a noun? And if it is, it's a noun phrase. And if it's not, there's no other possibility. This is not a noun phrase. It's not a valid sentence. But if so far we have found, say, an article followed by a noun, we've got a noun phrase, it's like, okay, this could be a valid sentence, provided it's followed by a verb phrase and a period. So let's see if this is a verb phrase, and we try one of these definitions, and why did I write plus or? And let's say it turns out to be a verb followed by an adverb. We say, okay, well, this is a verb phrase. Is it followed by a period? And we check to see if there's a period, and if it is, then we can say, okay, that's a valid sentence. Okay, so is it a noun phrase? We have to know, is it an article, adjective, noun, or is it an article, noun? So we need to define what these things are also. And these, I'm going to write separately. So an article is either a or the. So it's those particular collections of symbols. All right, an adjective. So adjectives modify nouns. So give me your favorite two adjectives. Or two people, give me your favorite adjective. We're playing Mad Libs.
Purple.
What is it?
Purple.
Purple, okay. So an adjective is purple, or someone give me another adjective. There's no wrong adjectives.
Hungry.
Hungry? Angry?
Hungry.
Hungry, okay, good. All right. So I want a pair of nouns. Cat. All right, give me another noun. Dog. Okay. Verbs, actions. Give me a verb, please.
Fly.
Fly. All right, and I'll take one more. Walk. How many people have played Mad Libs? Okay, cool. Okay, so adverbs are anything that modifies a verb. And they don't have to modify these verbs. So give me an adverb. Quickly. Give me one more adverb. Quietly, okay. Awesome. So these we can think of as being sort of terminal symbols, which are somehow different from these because each of these was defined in terms of something else that was defined in terms of something else, right? But these are actually just patterns of symbols, right? A verb is an F followed by an L followed by a Y or W-A-L-K, right? So once we are looking for a verb, we're actually just looking for a particular symbol. So these are somehow different from these up here. Okay, well, we can do a couple of things with this now. One, we can look at a sentence and see, is it valid in this language? So here's a sentence. A purple cat flies quickly. Let me make this flies. Don't worry about like proper English. So a purple cat flies quickly. Is that syntactically a correct sentence? Right? Absolutely. And how do you know? Because a purple cat is a noun phrase, flies quickly is a verb phrase. And how do we know that a purple cat is a noun phrase? Because it's an article followed by an adjective followed by a noun. And flies is a verb and quickly is an adverb. And so an article followed by an adjective followed by a noun is a noun phrase, and a verb followed by an adjective is a verb phrase. Oh, we got a period at the end. And so we have a noun phrase followed by a verb phrase followed by a period, and a noun phrase, verb phrase, period. That makes a sentence. Anybody here diagram sentences in school? So they didn't do it when I was in school. They did it before that, and I guess they do it now. That's really all we're doing here, right? So we can take this description of a language, right, of what a sentence is, and we can apply it to a set of symbols and say, is it a sentence, right? The other thing we can do is synthesis. We can use this to create sentences, and that's what Mad Libs is, right? So to create a sentence, well, we need a noun phrase followed by a verb phrase followed by a period. Noun phrase, we can pick an article, so we can say the. That's an article. And then we need an adjective, so we can say hungry. And we need a noun, so we can say dog. And then we need a verb phrase, which is a verb, so we can say walks. And we need an adverb, and we can say quickly. And we need a period, and we've constructed a valid sentence. So this is the basic goal, okay, to be able to describe things that are valid sentences under some language. But this is not a terribly convenient way to do this. Okay, it kind of works well for English, other than all the exceptions. But it's not easily formalized for things like programming languages. So we want a general way to do this. Okay, so we're going to go crazy with some definitions. So we're going to define a vocabulary, V, is a finite non-empty set of symbols. And we're going to describe a sentence over V, and sometimes we say a word over V. They're interchangeable, but a sentence over V is a finite length string of elements of V. So V is a set of symbols. A sentence over V is just some collection of those symbols in the particular order. Okay, a string of them. And it can't be infinite length. It could be empty though. Okay, so an empty string will be considered a sentence or a word. So in that case, we use a symbol lambda. That's the empty string. So a string consisting of 0 elements of V. And that's not the same as an empty set, okay? An empty string exists. It's a string. It just happens to have length 0. It's like the difference between in C, you can have a string which is equal to double quote, it's a string of length 0, but it sits somewhere in memory, right? As opposed to null, which is actually a null pointer, which if you try to print it, you get a seg fault. If you try to print a string that's just quote, it just prints nothing, right? So this is a string, it just has length 0. Okay, so now the good stuff. V star is the set of all words over V. So it's the collection of all possible combinations of finite length of symbols from your vocabulary. So imagine your vocabulary is just the letters A through Z. Okay, a word over V would be just some finite length collection of those symbols. So take any collection of those letters and put them side by side, you've got a word over that vocabulary. And then V star is a set of all possible words. So it's an infinite set, but each thing in that set has finite length. Okay. So V star is a really, really big set. Okay, so here's the definition we're after. A language over V is a subset of V star. V star is a set of all possible combinations of letters of any finite length. A language over V is the dictionary. It's the collection of those particular symbols that we consider to be valid. Okay, but more generally, it's just some subset of those symbols. What we're working towards is the set of symbols that we consider to be valid. So our question now is, how do we specify what a language is? You got your set of symbols, you've got the big uber set that contains all possible collections of sequences of those symbols, right, all the words, and we're trying to specify some subset of that, which we call a language. So English, for example. And so how do we specify a language? So one option is just go ahead and list all the words in the language. Okay, that's what we do with dictionary. You got some set of symbols, you're playing Scrabble, you want to know if this is a valid word or not, you open the dictionary, you look for it in the list. If it's in there, it's part of the language. If it's not, then it's not. And that works great for us. It works really, really bad for a compiler. Because a compiler doing this would need to have a dictionary of every possible C program. And then when you wrote a C program, it would just look and see in the dictionary if that C program was listed. And if it was, it would say, okay, that's a good C program, right? And that's obviously not feasible. Because the language of C is much, much larger than the set of words in the English language. So another approach lists some rules for a word to be in the language. So how do we do this in English? Well, if you have the letter Q, it's usually got to be followed by the letter U. There's a few exceptions. If you have a word, it's got to have at least one vowel in it. There's a few exceptions. You can list criteria that have to be satisfied for something to be part of the language. And you can kind of do that for a compiler to some degree. If you have a C program, it's got to have, I don't know what it's got to have. It's got to have curly brackets. It's probably got to have integer I somewhere, right? But it's still a little tricky to try to sort of come up with rules that will just take this thing and tell you if it's a word over it. So the approach we're going to work with is describe the grammar. And a grammar is basically a set of symbols and rules for producing words. So you're going to describe ways that you can create words in this language in such a way that we can take this unknown thing and we can say, is this producible using these rules? Okay, that collection of rules is what we're going to call a grammar. And we're going to describe that in detail. So, definition. So we're going to describe what's called a phrase structure or grammar. So we're going to call this grammar G, and it's a four-tuple. So it's an ordered collection of four things, which are sets we're going to call V, T, S, which is not a set, but we can think of it as one, and P. Okay, so V is the vocabulary. It's a collection of symbols we get to use. T is a set of terminal symbols. And so T is going to be some subset of V. So it's a set of special symbols from our vocabulary. S is a start symbol. So it's one particular element of V, so that's not actually a set, it's just an element. And then the real kind of action item P is a set of productions. Productions are rules we can use to change one thing into another thing. Okay, so let's get concrete now. Let's do some examples. So let's look at the following grammar. So our vocabulary is going to be the following set of 5 symbols. Little a, little b, big B, and little s. Our terminal symbols are going to be little a and little b. Our start symbol is little s. And our set of productions are going to be as follows. So I'm going to write little s arrow, big A, big B, little a. I'm going to write big A arrow, 2 big B's. And I'm going to write big A, big B, arrow, little b. So here's what we do. We start with the start symbol. Okay, so we begin with whatever the start symbol is, which is this little s. And we can apply any production rule that has an S on the left side. These are basically saying the thing on the left can be replaced with the thing on the right. So a little s can be replaced with big A, big B, little a. A big A can be replaced with two big B's, and so on. So if we start with a little s, the only production rule that can possibly apply is this first one, which says we can replace s with a big B, and a little a. And our goal is to start from S and use these productions to transform it into something that contains only terminal symbols. So S is not a terminal symbol, so we're not done. Big A and big B are not terminal symbols, so we're not done. But we'd like to apply some production rules and try to change this into something that contains just little a and little b in this case. So what can we do? Right, we have production that says big A, big B can be replaced with a little b. Well, here's a big A, big B. We can replace that with a little b. The A stays as it is. And now we've got something that's comprised just of terminal symbols. Since we started with a start symbol, we applied the production rules and we came up with a set of terminal symbols. This is a word in our language. So according to the grammar, this is a valid word. Was there anything else we could have done?
That would have been a valid word.
So we could have tried S goes to A, B, little a, and we could say A gets replaced by B, B. But there's no production rules that help us with that. So with this, it looks like this is the only thing in our language. All right, so let me modify this a little. And very soon I will start getting sloppy and taking some shortcuts, but for the first few, I'll be explicit. So let's add one more production rule. Big B can be replaced by little a, little b. So we still have that first word that we found where we took S and we replaced it with ABA, and we took AB and replaced it with B. And so we got BA. But now we can again try to say AB, or B is replaced by, A is replaced by BB. But we also have a rule now that says big B can be replaced with little a, little b. So each of these can become AB. And that last A carries through, and there's a string made up of just terminal symbols. So that's a word over our vocabulary. So this may seem kind of like awkward and forced and artificial, at this stage, but this will turn out to be a pretty useful way to spec out languages. So we need some more definitions. So suppose some word W0 is some string, which I'm just going to call L, followed by some middle piece Z0, followed by some other string, which I'm going to call R. So it could be, 5 symbols and 6 symbols and 2 symbols or something like that. But we can think of it as broken into these 3 pieces I'm calling L, Z0, and R. And suppose there's another word W1, which is the same string L, followed by some other string Z1, followed by the same string R. So we got 2 words, and they're the same in the beginning and the end, and the middle part may be different. Okay, so if Z0 to Z1 is contained in our set of productions, so if there's a rule that lets us change Z0 into Z1, we know that we could take W0 and we could change it into W1, right? By just applying this production rule to this middle piece, and the L and the R will be the same. Right, so this is what we've been doing in our little tree-like diagrams. So in this case, where there's a production rule to go from Z0 to Z1, then we say W1 is directly derivable from W0. And we write this symbolically with a double arrow. And it kind of feels like the right thing to do, right? We're basically saying you can change W0 into W1 by using some production rule. And so here we might have said something like S can be turned into ABA. And we could also write ABA can be turned into BBBA. So saying that this is directly derivable from that basically says that you can apply a production, turn the former into the latter. Okay, if W1 is directly derivable from W0, and W2 is directly derivable from W1, and so on, until eventually Wn is directly derivable from Wn minus 1, then we say Wn is derivable from W0. So it's not directly derivable, but it is derivable through a series of direct derivations. And we have a notation for that. Same double arrow, but we put a star on top of it. So that means derivable, but possibly not directly. And this thing here, we call a derivation. So Wn is derivable from W0, and this sequence of direct derivations from W0 to Wn, that's what we call a derivation. So going back to here, right, BBBA is derivable from the symbol S. And S goes to that, and that goes to that would be our derivation. So now we can take all of this stuff and express it succinctly. So, possibly our last definition for a little while. The language generated by G where G is this phrase structure grammar, we can write as L parentheses G. This is the set of strings of terminals terminal symbols derivable from S. So the language generated by G, or the language of G, is a set of strings of terminal symbols derivable from S. Or it's a set of words contained in the collection of all words comprised of terminal symbols, the set of W and T star, such that W is derivable from S. So this is what math does. It takes like 45 minutes of lecture and boils it down to like one equation. So that's what the language of a grammar is, right? The set of symbols in T star that are derivable from S. Put on a little light, 'cause it's getting really dark. It's still visible. All right, so let's see some examples. So our vocabulary will be S, big A, little b. As usual, the terminal symbols will be A and B. The start symbol will be little s. And the production rules will be S goes to little a, big A. S goes to B, little b, and big A goes to two little a's. And we want to find a language over G. So there's one word I can write down pretty quickly and say this is definitely part of the language. B. Because even in my head I can say, well, if I start from S I can get to B, and that's comprised of terminal symbols. So that's definitely part of the language. Is there anything else?
I think there's only two in the language.
There's only what?
I think there's only two in the language.
Okay, so what would the other one be?
S goes to A, big A, which can be turned into AAA.
And I think that's it. I think you're right. So that's not a very exciting language. It's got two things in it. It's no better than the last one we had.
It's got a triple A and B.
It's got a triple A and it's got a B. All right, let's make something more interesting. So our vocabulary consists of three things: start symbol, a 0, and a 1. The terminal symbols will be 0 and 1. The start symbol will be S. And our production rules will be S can be a 1 followed by a 1 followed by S, or S can be a 0. So what's our language look like here? It's definitely got a 0. What was the second one? Okay, so S can be a 1, 1, S. And S can be a 0, so it could be a 1, 1, 0.
It could infinitely loop by S goes to 1, 1, S.
Ah, so S can be 1, 1, S, and this S could also be a 1, 1, S. So it could be a 1, 1, 1, 1, S, and that S could be a 0, so it could be 1, 1, 1, 1, 0.
It could be any even number of ones followed by 0.
Yeah. So that's a little more interesting. Any even number of 1s followed by a 0. So every word in that language is finite length, right? There's no infinite number of 1s followed by a 0. It's always going to be a finite number of symbols, but it could be 10 billion and 12 1s followed by a 0, which is a 10 billion and 13 character long string, but that's part of the language also. So here we have a very simple definition, right? Vocabulary, terminal, start symbol, and productions, but we've produced an infinite language. Language with an infinite number of things that it recognizes. And with a potentially interesting rule because it's looking for things that are 0 mod 2, which could be kind of cool. All right. Getting the idea of this? So let's try another one. So 0, 1, big A, big B, and S. Terminal symbols are 0, 1. You're seeing a pattern by now, right? Start symbol equals S. And our production rules will be S goes to 0A, S goes to 1A, A goes to 0B, B goes to 1A, and B goes to 1. What's going on here? So sometimes you can stare at these and figure out something that's happening. Sometimes you just start producing words and that lets you figure out what's happening. Sometimes it's just bizarre. So let's play with this. If I'm not sure pretty quickly what's going on, I start making some words and see if we can figure it out from there. So what are some possible words in this language? We know we're starting from S.
1.
We could do 0A or 1A. How'd you get to 0, 0, 1?
A. You start with S, which goes to 0A.
Okay.
A can be translated into 0B.
Okay.
B can be directly translated to 1, which is a terminal.
All right, so there's a 0, 0, 1.
Looks like this only ends when B is translated last.
Okay, so B gets translated last. That's the only thing that actually goes into just a terminal, right? So what else could S go into?
Well, B can go into, if you take the last one, you can go into
B can go into 1A. So let me start bifurcating like this. 0, 0B could go into 0, 0, 1A. And then what does A go into? And what does B go into?
No, either one.
Right, could go into a 1 like that. Or we could branch off here. And this B could go into a 1A. And A, we got no choice. A always goes to 0B. And that B could go into a 1. And there's another terminal. Or we could branch off here, and so on. So we're seeing a pattern.
Yeah, every other one is 1, 0, exception the first one, either 0 or 1.
Okay, so yeah, we missed a whole possibility. We haven't gotten to a whole possibility yet, which is where S starts off as a 1A, right? And if it goes to a 1A, 1, 0B, 1, 0, 1, or we can branch off. We're going to get the exact same set of productions, but with a 1 in the beginning. So we can say dot, dot, dot.
The first two characters can either be 0, 0 or 1, 0.
Yeah. So
And
it's
the
like,
character is 1.
so it's
First character can be anything, and then past that starting at 0, which is 0, 1, 0.
all right, so let's break it up like that maybe. So the first character can be a 0 or a 1, and then it's a bunch of repetitions of 0, 1.
Yeah.
And it's any number of those. But we have to have at least one of those 0, 1s. So it's a 0 or a 1 followed by 1 or more 0, 1s. So something like a regular expression might look like this, right? We have either a 0 or a 1 followed by a 0, 1 followed by 0 or more occurrences of 0, 1. That's not actually a totally valid regex because asterisk works on a single thing. But that's the idea of it, right? And we'll find that we can actually go back and forth between regular expressions and phrase structure grammars. Because what's a regular expression? It's a way to describe things that are valid under some set of rules. When you write a regex and you say, I'm looking for something that matches this pattern, you're describing some criteria by which you're going to recognize or not recognize sets of symbols as being valid under that criteria. Right? That's what a regular expression is. It's a way to describe some possibly infinite collection of symbols that you're interested in looking for. So here's something that we might spin into a regex. So either character followed by 1 or more repetitions of 0, 1. And sometimes we might write this as follows. Could be a 0 followed by 0, 1 to the n, where n is bigger than or equal to 1, or a 1 followed by 0, 1 to the n. So we're kind of loosely applying an exponent notation. Saying n is bigger than or equal to 1 means we need at least one of these. But if n is 2, it's 0, 1, 0, 1, and so on. All right, well, that's one direction of working with languages. This is the analysis direction. Okay, it's looking at a description of a grammar and then figuring out what's the constituents of the language. So that's like state machine analysis. What comes next is synthesis. Suppose you know what the constituents of a language are, can you construct a phrase structure grammar to describe it? So that's the next thing to think about, is constructing a grammar. And we'll do one or two of these, and then I'll leave you to think about it. So suppose we know that the language of this grammar consists of the following. The empty string, a 0 followed by a 1, 2 zeros followed by 2 ones, 3 zeros followed by 3 ones, and so on. Which we could write in our new shorthand as 0 to the n, 1 to the n, where n is bigger than or equal to 0. So if n is 0, this is no zeros followed by no ones, that's the empty string. If n is 1, it's a 0 followed by a 1. If n is 2, it's 0, 0 followed by 1, 1, that's this, and so on. So we'd like to construct a phrase structure grammar whose language looks like this. So let me start you. We're going to at least want 0 and 1 to be in our vocabulary. We're going to want some kind of start symbol, S. We may want other symbols in there. Our terminal symbols will be 0, 1. Our start symbol will be S. So let's play around with possible production rules. So thoughts.
You have to have the start symbol, right? So that has to, you do whatever you pick whatever you want.
Yeah.
A, B.
Okay. So we can throw an A and a B in here.
And then there could use just A and B.
Translate to AA.
Okay. So there's no algorithm for how to do this, right? It's not like we can look at this and we can just apply some operation to this and come up with a set of production rules. It's a trial and error kind of thing. It's like designing state machines, right? Well, state machines we actually had an algorithm for, but in the beginning we didn't, right? So it's playing around with different production rules, and the more analysis you do, right, the more you look at phrase structure grammars and break them down into languages, you start to see things like, oh, it's useful if we have A go to AA, right? So we can try that. So it's a trial and error thing. And the more you trial, the less you error usually. And it starts to make more sense at some point.
A could go to AA and A could go to 0 if we're going like that.
I think that A needs to go to AAB so we have the same number of B's.
Ah, okay. So we need to make sure we have the same number
B go to B, yeah.
of zeros and ones. So B go to BB, and we want A to go to AAB.
Only that won't work because then you can pick an A close to the beginning and you have a B stuck in the middle and B has to go to 1.
Right.
Ah,
So we'd have an even number of A's and an even number of B's, but they're not necessarily going to be the same. But we're definitely getting there.
Well, you have E goes to A, E, E.
B goes to ABB.
I think you would want either just the A transform or just the B segment. And maybe you can just have.
A could go to 0 or A could go to 0A.
But I mean, I think you need either the B set or the A set where you remove the possibility from going to a 1 or possibility to go to
Okay, so we'll make this green. So what do you suggest here?
So I suggest S goes to AB, A goes to AAB, and then A goes to 0 and B goes to 1.
All right. So we've definitely got a 0, 1. We could go to AAB, which would get us 0, 0, but that could get us 0, 0, 1, followed by a B. Okay, I like this. So let's make some words. So A could be A, B, followed by B. And then A could again be A, B. But then this A would,
Yeah, the problem is that you can go wrong.
yeah. But we've still got the same number of A's and B's.
I guess you'd have to transform AB.
Yeah, that was A.
You'd have to transform AB that way we could restrict it to the center.
So still S goes to AB.
Yeah.
And then what do you suggest?
AB goes to AA, B, and A goes to 0, or B goes to 1. So they can't change without both changing.
Okay. So S goes to AB, AB goes to AA, BB. That I kind of like. So let's try S goes to AB, goes to AA, BB. And then this middle AB, this could either go to 0, 0, 1, 1, or this middle AB could come down to AA, BB, followed by a B. So there's your 3. I think this works good. And so we can keep doing this. And there's our 0, 0, 0 with 4 ones.
Incorporate
Cool.
empty string.
So this will not get us to an empty string, but that's a pretty easy one. We can just say S can also go to lambda. And so now,
Was that a lambda in the beginning?
yeah, so it could be a totally empty string in the language, or it could be 0, 1.
So does the lambda, is that the vocabulary, or is that just
No, lambda is a string comprised of 0 symbols. So it's a 0-length string. So it's not part of the vocabulary, but this is saying basically replace S with the empty string. So it's not technically a terminal symbol, but the empty string is comprised of terminal symbols. It just happens to be no terminal symbols. Okay, so that looks good. I like it. All right, cool. Nice work. So we will leave it there for now, and Friday we will we'll come back to this and we'll look at it a little more. We'll play with a couple of other constructions, and then we're going to talk about other ways to analyze syntax, something called Bacchus-Naur form. And then we're going to start talking about finite state machines. So we'll flash back to 250, but I promise we won't make any flip-flop tables. So it'll be good. All right, I'll see you then.